For today's lesson, we are going to learn about exponential functions. Our learning targets for today are for you to be able to say, I can write an exponential function from a table. I can graph an exponential growth function from a parent function reflection or using a parent function reflection translation table or PFRST table. I can describe the transformation of an exponential function from its parent function, identify the domain and range. We're going to skip end behavior for this here. I can use exponential growth models to make predictions about real world occurrences, as well as find the ending balances of accounts given an interest rate and how often interest is compounded. So we have a lot that we are going to be learning in this lesson. This first video is just going to be over page 1, which is just going to be the tables. So an exponential function means that instead of x being in line with all of the other constants, instead, x is now going to be in the exponent position. And a very basic exponential function is written in the form of y is equal to a times b to the x power. That's where, if it's in this format, this simple form, your A value represents your starting amount whenever x is equal to 0 when you're analyzing a table. So that starting amount is going to be located at the ordered pair 0, your A value. Your growth or decay value depends on whatever the value of B is. B is also known as a multiplier. It is how quickly value or data is growing or decaying. It is going to be the number that you are going to be multiplying your y values by in the table. So when we're analyzing tables and you're looking at the change of your y values, you're going to notice that unlike a linear or any other polynomial function that we've analyzed this year, where we analyze the differences, either the constant first differences, second differences, even third differences. This time you're going to notice that the differences are inconsistent, and instead you'll notice a pattern of multiplication. You'll be multiplying by the same number each time in order to get to the next number. Now, an exponential growth function is a function that is written in the form of y is equal to a times b to the x power. And that's where your a value is bigger than 0. And any number that's bigger than 0 is automatically a positive number. So if you have an a value that's a positive number and your b value is bigger than 1, then that indicates that you have a growth function. So you're going to notice that your b value will be like 2, 3, 4, 5, 6, etc. You also might notice that it might be like an improper fraction, like 5 over 4 is technically bigger than 1. So those instances, we have ourselves exponential growth. Exponential decay is also written in that form of a times b to the x power, where a is once again greater than 0, where you have once again a positive a value that's in front. But your b value this time is in between 0 and 1. And what you're going to see is you're going to see a small fraction. When it comes to both of these, identifying whether or not you have growth or you have decay, it's all going to be based on the b value. And for both of these instances, your a value is positive. It will always be a positive number, at least to start. Once we get into an a value that's negative, then suddenly the growth and the decay definitions start to vary, and it becomes a little bit different. And that's something that we're going to explore a little bit later in this unit, not necessarily in this lesson. So in example number 1, we want to determine the equation from the table. So that means that we need to identify our a value and we need to identify our b value. So our a value, remember, that's whenever x is equal to 0. So we always want to look at the table and identify where is x equal to 0. And fortunately for us, we can very quickly see that when x is equal to 0, f of x is equal to 2, and this is going to be our a value. It's the value of y when x is equal to 0. So far, when it comes to writing my equation, I have y is equal to 2. And now I need to analyze the table. What am I doing each time in order to go to the next number? What am I multiplying by? So how do I go from 2 to 12 and 12 to 72 and 72 to 432, etc.? And hopefully you're seeing it right away, saying, well, you're just multiplying by 6. 2 times 6 is 12. And what you'll notice is that consistently, you're going to be multiplying by 6 each time. And this value of 6, this is your b value. So far I have 2 times 6, and this is going to be raised to the x power. A misconception is to call this 12 to the x power. But unfortunately, we are sophisticated Algebra 2 with trig students. We know the order of operations say you have to take care of exponents first. And since we can't take care of exponents, we keep the power separated from our a value. This is an exponential growth function. And the reason why this is a growth function is because simply the multiplier of 6 is bigger than 1. That's what makes this exponential growth. Let's go ahead and look at letter B. Letter B is another one of those convenient problems because we can clearly see what our a value is going to be. Our a value is going to be equal to 27, and that's located whenever x is equal to 0. So I have y is equal to 27 times, and now I need to find my b value. So this time around, it looks like my values are progressively getting smaller. And analyzing the area where the numbers are easier to work with, what do I have to do to go from 27 to 9 and 9 to 3? You might be saying to yourself, well, I'm dividing by 3. And consistently, that is true. We're dividing by 3 each time. But remember that your b value is a multiplier. So the thing that I want you guys to note is that dividing by 3 is equivalent to multiplying by a third. Remember that whenever you are dividing by a number, you can always multiply by its reciprocal and still end up getting the same exact result. And our b value is all about what are we multiplying by. And so in this case, we don't want to say the number 3 because that would indicate that our values would be growing as x increases. But that's not what's happening here. They're decreasing. So therefore, 1/3 is going to be our b value. Notice that this number is in between 0 and 1. And that means that this is going to be an exponential decay function. So my equation is going to be y equals 27 times 1/3 raised to the x power. I strongly recommend that you put 1/3 into parentheses, and that's so that in the event that you are calculating values by hand, it reminds you that not just the numerator is being raised to the x power, but also the denominator is being raised to the x power as well. This is considered exponential decay simply because the multiplier is 1/3 and smaller, the multiplier is 1/3 and it's between 0 and 1. Finally, letter C. If we look at the table, I do not see where we have an x equals 0. So finding our a value is going to require a little bit more thinking. So because of that, we're going to go ahead and move on and just leave a little bit of space, and let's go ahead and try to find our b value. Now we're going from 25 to 125, 125 to 625, et cetera, and it looks like we're growing really fast. So one way to figure out what you're multiplying by is to divide. 125 divided by 25 is equal to 5. And it appears as if we are multiplying by 5 each time in order to get to the next number. Now, I don't know what my a value is, but I do know that I'm multiplying by 5 each time to get to the next number. So 5 is going to be my b value. And now what I need to do is I need to somehow figure out, yes, I think I'm going to do it like this. I somehow need to figure out how to figure out when x is equal to 1, what that value is, and when x is equal to 0, what that value is. So if going forward, if as x gets bigger, we're multiplying by 5, What do you do when your x is getting smaller and you're going backwards? Well, you're going to use the inverse operation, and the inverse operation of multiplication is division. So like, what did we multiply 5 by in order to get 25? So when we go backwards, we're going to divide by 5. So going backwards, 25 divided by 5, that's 5. And I'll go backwards one more time, divided by 5. 5 divided by 5 is 1. So in terms of my a value, it looks like my a value is simply going to be the number 1. So y equals 1 times 5 to the x, it would be our answer. You can also write this as simply y equals 5 to the x as well. Most of the time, this is how we express it, y equals 5 to the x. Both ways are absolutely appropriate, and once again, this does indicate that we have growth. And the reason why this is growth is because the multiplier is 5 and it is bigger than 1. All right, let's go ahead and look at example number 2. In example number 2, it's asking you to create a table or create the table given the following equations. Then determine if the equation represents exponential growth or decay. So when it comes to creating a table of values, I would strongly recommend selecting -2, -1, 0, 1, and 2. There are a couple of approaches for this. One approach is to use some facts that 0, 8 is going to be our starting point. So we always refer to it as a starting point. So 0, 8. And as we move forward, we can use our multiplier of 2. 8 times 2, that is 16. 16 times 2 is 32. And then going backwards, we divide by 2. 8 divided by 2 is 4. 4 divided by 2 is 2. So this 0, 8 is always our starting point. Going forward, we use our multiplier. Going backwards, we use the inverse of our multiplier. So instead of multiplying, we would divide. This is one approach. Another approach is to simply substitute. Like, let's let x equal -2. So then that would mean that we would go y is equal to 8 times 2 to the -2nd power. Now, 2 to the -2nd power is not happy where it's at, so I'm going to bring it down to make this 8 over 2 squared, which is 8 over 4, which is 2. And voila, look, isn't that what we ended up getting? You plug in -2, your output is a +2. And you can do that each time for every single value. Both approaches are absolutely appropriate and correct for these types of problems. This problem is considered an exponential growth function. And the reason why it's exponential growth is simply because our a value, which is 2, is our multiplier. And our multiplier of 2 is bigger than 1. It's bigger than 1. Let's go ahead and look at letter B. For letter B, we can use this exact same approach. In this problem, I'm going to let x equal -2, -1, 0, 1, and 2. I know that my a value is 20, so 0, 20 is going to be my starting point. From here, my multiplier is 1/2, so I'm going to multiply by 1/2 each time in order to get to the next number. 20 times 1/2, that's 10. 10 times 1/2, that is 5. And then I can use this value going backwards. So instead of multiplying by 1/2, I would divide by 1/2. But remember that dividing by 1/2 is the same as multiplying by the reciprocal. That's equivalent to multiplying by 2. 20 times 2 is 40. 40 times 2 is 80. And if you think about it going forward, 80 times 1/2 is 40. 40 times 1/2 is 20, and so on. This is considered exponential decay, and that's because our values are decreasing as they go down. And this is decay also because our multiplier of 1/2 is between 0 and 1. So that is the end of our information when it comes to tables. The next video lesson will be all about the graphs. If you have any questions over anything that I've talked about, please feel free to email me. Otherwise, I hope you have a wonderful day.